Welcome to Higher Structures seminar series of Feza Gürsey Center for Physics and Mathematics. Today our speaker is Simona Paoli from University of Aberdeen. She will tell us about the weekly globular approach to higher categories, and we thank Simona for delivering this talk. Please, Simona.
Okay, thank you very much for the kind invitation. I think this online seminar on higher structure is a really good idea, given how many people from different fields are actually working with higher structures. I was myself involved last summer in a big program at the Isle of Skye in Scotland, funded by the Isaac Newton, where we brought together lots of people from different fields during higher structures. But of course, the online medium is particularly suitable for this because we are all constrained by lack of time and lack of money. So I'm very happy about this initiative. So my talk is going to be about some of my work in this area in the last sort of 5 or 6 years. I've done a lot of work, including writing an original research monograph on this. Some of this course is highly technical and would not be possible to present this in an hour. So what I want to try and do is give you some of the main ideas and the main concepts. And then I will tell you some precise references, and especially maybe graduate students, if they want to learn more, they will have a way to do it. But as I said, in 1 hour, there is just so much that I can do. So let's start with a general dichotomy between what we call a strict N category and a weak N category. So you know that a category has objects and morphism, a strict two category has objects, morphism, and two morphisms, and you just carry on this to dimension N. But the idea of strict means that these higher morphisms compose in a way that is associative and unital. Okay, so like in a category. And there are identities, and these identities obey the unit laws. So there's really not a lot going on in a strict N category, and formalizing this is something that is quite easy. You can do this by iterated enrichment. Say a strict two category is a category enriched in cat. And then you keep doing this. You take a category enriched in categories, and so on. So from the formal point of view, these are easy to define. But if you look at examples of higher structures coming from a variety of fields, and I will say a little bit more about this in a moment, you see that strict N categories are not enough. And so you want a more elaborate notion where these higher morphisms have compositions that are not associative and unital. They are associative and unital only up to an isomorphism, so a cell or a higher morphism in the next dimension, in a way that is well behaved. We call this coherence axioms. So there is this first big difference between the strict world and the weak world. But there are also other differences, and I'm going to very broadly talk about this in the next slide. So various types of higher structures. I have talked now about higher structures that have objects, one morphism up to n morphisms, but you can also have higher structures where you carry on with the dimensions, okay? So you have weak omega categories where you have morphism in every dimension, and these are the widest possible because all the compositions are weakly associative and weakly unital. And when you have invertibility of these higher morphisms, we call them groupoids. So you have weak N groupoid, weak omega groupoid. But then we also have an intermediate concept, which is called infinity N categories, where you have weak invertibility only after dimension N. As you're probably aware, these have been very important, especially mathematical physics, were used by Lurie and other people in connection with topological quantum field theory and the proof of the coordinate hypothesis. Now, one of the things that I mentioned earlier is why do we need this weakness? Why can't we just do everything with strict N categories? There are many examples that show you that strict world is not enough. One is homotopy theory. If you have a topological space, you know that you can break it into smaller parts, which are called N-types. These are excuse me, spaces with trivial homotopy groups in dimension higher than n. If you want to model this algebraically, it's not enough to use strict n groupoids. Sorry. And there are explicit counterexamples, just a sec. Explicit counterexample for which, for example, if you take a space with non-trivial weighted products, you can. There's a lot of dust in this room somehow. It is affecting my throat. So you cannot model the three type of this space with a strict three group, okay? And in TQFT, you have similar phenomena. You cannot model high-dimensional coordinates categories using strict n categories. There are also examples from logic. The structure of identity types in Martin-Löf type theories cannot be modeled by strict n groupoids. Okay, so you have all these concrete examples coming from different areas that call for the need of weak higher structures. But what is the problem? The problem is that in dimension 2, there is a notion of a weak 2 category that you can give by an explicit listing of the data and this coherence axiom. So this is the classical notion of bicategory due to Benabou. Has this been done in dimension 3? Yes. Gordon, Power, and Street had the notion of tricategory. Now, if you open the monograph of Gordon, Power, and Street, and you look at the coherence axiom of a tricategory, people tend to get quite scared. Why? Because they are much more complex. What about n equals 4? People tried to write down an explicit list of coherence axiom for what should be a weak 4 categories, and they failed and failed and failed. In other words, the approach to higher categories using an explicit form of coherence axioms becomes too complicated after dimension 3, okay? And this is why people took a different approach. And one of these approaches is the so-called modeling approach. In other words, it's the following. It's like, I give you a combinatorial machinery that encodes the idea of a weak n category or a infinity n category, but all the coherence axioms are automatically encoded in the machinery, okay? You don't have to write them down precisely. And one good test to say, is this combinatorial machinery really describing what you want, is the so-called homotopy hypothesis, which is really a theorem that should say, look, you have a subcategory of weak n groupoid that gives us an algebraic model of n types. Okay, so any questions so far? Is the kind of big picture clear? What is the modeling approach? Now, Emily Riel and other people have also more recently come up with a different approach to this so-called axiomatic modeling dependent approach. I have full respect for that, but this is not what I'm going to talk about. I do believe that the modeling approach is still quite important because it tends to be very explicit and can be good in applications. So what I'm going to talk about today is a particular approach to truncated n categories, so what I call weak n categories, using simplicial and multisimplicial objects. So what do we need? Sorry, there was a question? No. I cannot hear very well. Sorry, I really cannot hear very well. What should I do? Can I carry on? I'm not really sure.
Please carry on. Someone's mic
Okay,
was open, I
the
believe.
mic. Okay, okay. I'm happy to be interrupted, or otherwise we can have questions and
Uh,
answers at the end.
Thank you.
Okay, so what do we want by our machinery? We want a way to encode the set of cells in dimension 0 up to n. The behavior, I'm really sorry about this cough. The behavior of the compositions. And we also want some notion of higher categorical equivalences. And it turns out that using simplicial and multi-simplicial objects is a good environment for developing this. And I will talk about three types of models, and I will collectively call this model by SIG-N, meaning Siegel type model. Now, I wonder how many people know about simplicial things in this audience. Ilan, what do you think?
Well, almost everyone has some idea probably, but maybe just one or two words would be enough.
Yeah. Okay, that's good. That's very helpful and very reassuring. Okay, so what is a simplicial object? It's a functor from delta up into a category C. Delta is the simplicial category, the one that people use to do simplicial sets. And C for us at the moment can be just any category with pullbacks. There is a fundamental notion for any simplicial object. It's a notion of Siegel maps that comes from this commuting diagram. Here, xk, k has these maps going to this bottom part. And so if you take the limit of the bottom part of this diagram, which is this iterated pullback, you have a unique map from xk to this limit. This is called Siegel map. Why are Siegel maps a very good thing? Because we can use them to characterize nerves of categories, or more generally nerves of internal categories. So what is an internal category in C? It's like a category, but instead of being in sets, you live in C, okay? So you're going to have not a set of objects, but a object of objects that lives in C, a object of arrows, and so on. So in the same way that we have the nerve of a small category, which is a simplicial set, we have the nerve of an internal category, which is a simplicial object in C. And then you can ask, when is a simplicial object in C the nerve of a small... I'm really sorry. When it is a simplicial object in a C, a nerve of a small category, if and only if all the Siegel maps are isomorphism, okay? Now, this very simple thing is actually very important if you think about it, because it means, oh, I can now think about a category as a simplicial set, right? Satisfying additional conditions. Now, one good thing about this simplicial stuff is that you can take products of delta. So a multi-simplicial object is a functor from the product of n copies of delta up, which I denote delta n up into C. And you can think about this as a simplicial object in n minus one fold simplicial object in n different ways. Let me draw you, okay, I'll draw some picture later, okay? So you have multi-simplicial set. And what is good about n-fold categories? So let me define them first. So you start with sets, then you do categories, then you do categories internal to categories, and then you keep doing this, okay? And you will agree that this is a deceptively very, very easy definition. So you may think that n-fold categories are easy. The only thing that is easy about n-fold categories is their definition. It's a very, very difficult notion to study. Okay. Now, in which way is this different than a strict n category? It is quite different. They are not the same thing. And I will illustrate this with some picture in a moment. Okay. Now, what you can do from these n-fold categories, you can iterate the nerve construction. And this gives you a multi-simplicial object instead. Or you can stop one level down and then you go from delta n minus 1 up into categories. So you can do this for n-fold categories, and you can do this from strict n categories. So I want to show you some pictures, okay? So this at the left is the picture of the two-fold nerve of a double category. You see, a double category will have, and you can look at the right, the geometric picture. You have objects, vertical morphism, horizontal morphism, squares. And you see that you have two ways to compose, horizontally and vertically. So this nerve is just taking all the composites of this stuff. So it's a very, very geometrically appealing picture. And now let me show you the three-dimensional case. So this is a picture of a threefold simplicial set, right? So we have three dimension now, so we can use the three-dimensional Euclidean space. And this is what it looks like. And you won't be surprised to see that there are cubes appearing, right? Because a square of square is a cube. So this is the threefold nerve of a threefold category. And so you can stack this cube on top of each other's, along each other's into different ways. So again, very appealing, this picture, very symmetric. Everything is the same in all the three dimensions. Now, this is for the 2-fold category and 3-fold categories. But what if we asked about strict n categories? Well, how can we describe strict n categories using multisimplicial sets? Well, in fact, I'm going to do the following. Instead of giving you this definition, I'm going to give you the picture first. So let me show you this picture. So this is the picture. Remember this picture here. Okay, remember this picture here. So what you do, you see this. Do you see my mouse, by the way? Yes, you do see it. Okay. So look at this structure here. This is the nerve of a category. And imagine that this category was discrete. That means all these vertical maps are identities. What does this mean in terms of these pictures? It means that these squares, you collapse the sides. Yeah? So let's now look at this. Right. So this is what happens. The vertical category here is discrete, and you collapse everything. What is this? This is the double nerve of a strict 2 category. You see how it works? And now we try to do the same for n equals 3. So this was the picture. And now we want to say that all this red thing here is a discrete category, and all these sides, this one and this one, are discrete. So let me show you the picture of what happens when you do that. This is what we get. So you have coins, you have arrows into different directions, you have globes, and then you have a globe of globe. What is a globe of globe? It's a sphere, yeah? So this is the geometric picture of the threefold nerve of a strict 3 category. Yeah, happy with that? Now, this is not difficult. It's an exercise that you can give to a first-year PhD student. It's surprisingly useful because in this type of theory, you want to have some geometric intuition about what's going on. And this type of description is very useful for that. So now that I have given you some intuition, we can come back to the more general statement that was, okay, I was trying to say, how can you describe the strict 3 category multisimplically? You say all the Siegel maps in all directions are isomorphism, and then you need to ask this discreteness in all these places, okay? This discreteness is the thing that is responsible for the globular shape of your structure. So the precise mathematical way to write it down is like I have in the slides. If you don't follow all the details at this point, you can probably look at them later. The important thing is you understand that this is responsible for the globular shape. So it won't be a surprise that we call this condition the globularity condition. Why do I insist of this? Because in the new way of thinking about weakened categories, I look at the globularity condition and I weaken that. So instead of having globularity, I use what I call weak globularity. Okay, so there are other things that you can talk about for a strict n category. There is a truncation functor from strict n category to strict n-1 categories. Again, you can look at the technical details, or I can just tell you what is the idea. The idea is very easy. You take the top invertible cells, yeah, and you mod out by them. So it's like squeezing by the top isomorphism. So it's not very surprising we have this, what I call truncation functor. And we have a notion of higher categorical equivalence, because if you have a morphism of strict n categories, you can say it's an n equivalence if when you truncate, you have an n-1 equivalence. It's an inductive definition. And locally, it's an n-1 equivalent. Again, it's an inductive definition. It takes a while to absorb the technology, but the idea is, remember that an equivalence of category is a functor which is fully faithful and essentially surjective on objects. This is just a higher categorical generalization of that, okay? With condition A being the higher categorical generalization of fully faithful, and condition B, a generalization of, condition A, and condition B being generalizing essentially subjective on objects. Okay, so here is now the picture that we had, I've just been talking about, is the left-hand side, right? So we had multi-simplicial embedding, an inductive definition, truncation functor, a home, n-1 categories, and equivalences, globularity condition, the Siegel condition. What do we do on the right-hand side? On the right-hand side, we use a very similar technology. So we are going to be embedding ourselves inside n-fold simplicial sets. We are going to still have a truncation functor built more or less in the same way. The n equivalences have the same definition. What changes is that instead of having the globularity condition, we have what we call a weak globularity condition. And also we have a different Siegel condition. So what is the idea of weak globularity? The idea is the following. What's the sort of closest approximation to a discrete structure? Okay, think about, well, depends whether you are more categorical or topological. Think about a category. A category which is discrete means that all the morphism identities. So a category which is very close to being discrete, but not entirely discrete, could be a category that is just equivalent to a discrete category. What does this mean? Well, a category which is discrete is a groupoid. A category equivalent to a groupoid is itself a groupoid. So what does it mean to have a groupoid which is categorically equivalent to a discrete one? Well, remember that a groupoid is a space, right? It's a one type. So what does this mean? It means that it's a space with only zero non-trivial homotopy groups. So if you're more of a topologist, just think in these terms. It's something homotopically discrete. If you're more of a category theorist, we call these things an equivalence relation, okay? So it's a groupoid where not all the morphisms are identities, but between any two morphisms, between any two objects that are distinct, there is at most one morphism, which is invertible, okay? So it's like a very minimal fattening of a set.
I think there is a question.
Yeah.
Jenna, please ask your question.
Yeah. Okay. Should I find this in the chat? Except that I'm not very good with Zoom. Could you maybe ask me? I don't see the question.
He raised his hand because
now okay, my voice coming?
yes.
Yeah.
In the definition of homotopy discretization.
Yeah.
Okay, you understand my?
No, I didn't hear it. I just think you want to ask something about this homotopically discrete, but I don't understand what you want to ask. I didn't hear it.
Okay. You can continue. Okay. Thank you. Okay. No problem.
So maybe he will ask later on.
Yeah, okay. But let me just give you a small example. Think about a groupoid with two distinct objects and just one invertible arrow between them. Okay? This is an example of a homotopically discrete category. It's a groupoid which is not discrete, right? Because there is a non-invertible arrow. There is a unique non-invertible arrow between the two objects. So this is a kind of fattening of something discrete. Now, this comes with a map, right, from X to the discrete category on its set of connected components. In this example, right, we just go from this two object thing, you just collapse them, and you take the discrete groupoid on that. Now, you can carry this idea to higher dimensions. And perhaps I should I want to skip the formal details because there's probably not the time. But just let me say that there is a way you can iterate this idea of an equivalence relation inside an equivalence relation inside an equivalence relation. So you get to this idea of a homotopically discrete n-fold category, which, again, if you are more of a topologist, is just like an n-fold fattening of a set. So homotopically, you're not really adding information. Categorically, you are adding some equivalence relations in all the directions. So the idea of the Siegel type model using weak globularity is that instead of saying you have these discreteness conditions in all the places where in a strict n category you had discreteness, you say in those places you have homotopical discreteness, right? So for example, for a double category, we say the category of objects, let me go back to the picture, the category of objects and vertical arrows here. Oops, sorry, it was this picture. Okay, this picture on the right. Yeah, here the category of objects and vertical arrows was a discrete category, this thing on the right here. Instead, we're saying, no, we want this right-hand side to be homotopically discrete. Yeah, this is what weak globularity means. But that's not enough because we want to add some conditions. Okay, sorry. Before I carry on, I like to say what is the role played by the kind of set of objects now, because if you now have something homotopically discrete, what should be the set of objects? Well, the set of objects is the set of connected components, okay? But then you have a problem with saying, how do my compositions behave? Because remember that we are trying to define a weak structure. And to define a weak structure, we want the composition to be weakly associative and weakly unital, but in a good way, in a coherent way. So the story is that there is a way to do this by what I call this induced Siegel map. So there is this map that goes, okay, so here, this was like the usual diagram for the Siegel condition, but instead of going down to x0, we compose x0 to this functor from, remember, x0 was homotopically discrete, so it comes with a map to the set of connected components. This also holds in high dimension, yeah? So you have this diagram, and then you can say, well, let's look at the limit of the bottom part of the diagram, which is this iterated pullback over x0d. And then we have a functor from xk to this limit. And this is what we call induced Siegel map. So in dimension, say, 2, right? This would be a functor between categories. We ask that this functor is an equivalence of categories. If you work in dimension n, it will be an inductive definition. So we ask that this is a n-1 equivalence, because inductively we say we have done everything already in dimension n-1. So these are really some sort of general idea. You can also define the n equivalences in a way which is formally analogous to strict n categories, and then you can also, like complete the inductive step. Now, it turns out that this machinery gives rise to three what I call Siegel type models. So let me illustrate the differences here. The first one is the so-called Tamsamani model that was actually one of the very oldest examples of models of weekend categories. Tamsamani was a student of Carlos Simpson at the University of Nice, and he introduced this, I think it was in the 80s. Carlos also wrote a book about this model, introducing a model structure for it. So in this model, you have the globularity condition, like in strict n categories. But the difference is that all your Siegel maps are weak, okay? So they would be equivalences of categories in dimension 2, and higher up, there would be n-1 equivalences adopting the inductive approach. The second model is the one I have introduced, and it's called weakly globular n for categories. Here I'm doing something different. I'm saying instead of globularity, I introduce weak globularity in the way I have kind of sketched, but I am keeping all my Siegel maps isomorphism. So I'm working with an n-fold category. Then you have the induced Siegel maps, which are n-1 equivalences, okay? So why are these two structures very different? Because in the first structure, the Siegel maps are not isomorphism. In the second structure, they are isomorphism. So the second structure is a rigid structure, but yet it encodes the idea of weekend category because I relax the globularity condition. And then there is a common denominator, which I also introduced. So you can say that both the Tamsamani model and weakly globular n-fold categories are part of a bigger structure, which I also introduced, where you relax both the Siegel maps and the weak globularity condition. You may ask, why on earth did I come up with this? It's not that I woke up a day and I thought, let's do weakly globular n-fold category. It didn't go that way. These things arose from homotopy theory, okay? I started working on this quite slowly, actually, from, I don't know if you've ever heard of a paper of Jean-Louis Laudet. Well, Laudet was one, but also there were other approaches about modeling connected n types with Cartan groups, okay? And when I was in Sydney working in the Macquarie group, I started asking myself, how does this relate to the Tamsamani model? And I found the answer, but this answer was for path-connected n types. So everything was internal to the category of groups, where you have semi-direct products, all sorts of very special things. That I proved, that's where I discovered first time the notion of weak globularity as arising in simplicial homotopy theory. Then I worked with David Blanc, an algebraic topologist, and we extended this to the non-path connected case, at which point I started, and it's a very non-trivial thing to do, but I started believing that there's something more to this. I think this is a special case of a new model of weekend categories. And we did this with the red prong for n equals 2, and then I extended it for any n. The case n equals 2 and the case n bigger than 2, they are very different because this is a general fact in higher category theory. N equals 2 and n bigger than 2 very often is a big, big jump in difficulty. So here are the main results. Basically, what I show is that all these three models are suitably equivalent, okay? And in particular, because the Tamsamani model satisfies the homotopy hypothesis all the other three also satisfy the homotopy hypothesis. And so that means in particular that you can use n-fold categories with these additional conditions to model weak n categories. And I wrote down the explicit comparison functors. None of these is trivial. It's interesting, and I have no chance to really go into the technical details here, but it's interesting that there is the notion of pseudo-functor from a small category into cat that plays a fundamental role in this theory. And in the groupoidal case, as I said, I was able to identify a subcategory of weakly globular n-fold categories that are an algebraic model of n-types. And I would also like to say a little bit more in detail, how do you do the groupoidal case? Again, you proceed inductively, okay? All these structures are inductive. So in dimension n1, we have just groupoids. Then you say, well, suppose that I have the groupoidal structure at level n-1. I just look at the home n-1 categories, and I ask that these are groupoidal. And then I do this truncation, and I impose that it is groupoidal, okay? So this is how you do the definition. One interesting thing about this homotopy hypothesis is that I told you I did this work somewhat independently with David Blank, where we had written a functor from a space to one of these groupoidal gadgets. And actually what was in the paper with Blank was a slightly more kind of special structure, what we call a weakly globular n-fold groupoids. The good thing about that functor is that it's very, very explicit. Basically, what you do is you take your space, you take the Can complex, which is, sorry, you take its singular functor, which is a Can complex. You do something to it, which is very combinatorial, very explicit, and then you take a left adjoint from n-fold simplicial sets into n-fold groupoids. And you get one of these things. So when people ask me, give us an example of this, here is an example, okay? It's in my paper with David, but I haven't got the time to really go into the technical details. But this is to tell you how I got to these structures. I mean, it's not some sort of general nonsense. It is something that really arises concretely from homotopy theory, okay? Then, so doing this took more than 5 years, and I've written a research monograph on this. But I've always been asking myself this question: what is this weak globularity? What does the weak globularity condition really encode? Okay. And it's always good to start in low dimension. So I started asking myself this question in low dimension. So let's take a weakly globular double category. So we know that the category of objects and vertical arrows is homotopically discrete. What does this mean? And what's the story here is that years ago, I mean, back at the time I was at Macquarie, Joachim Koch came up with a paper where he talked about weak units using, and he introduced this interesting category called fat delta to talk about models of higher categories that are somewhat special because they have weak units law, but everything else is strict. So the compositions are well behaved, they are strictly associative, but only weakly unit. And he called them fair N categories. So why was I particularly interested in that paper? Because even if you look at the case N equals 2, so fair two categories, what happens is that the category of weak units in Koch paper is homotopically discrete. Now, you know, it was too much of a coincidence to be just a coincidence. And I've been thinking for years and years, how does fair two categories relate to my model? And so I managed to answer this question. Again, it took a long time because I had to understand many new things about this fat delta. So now I'm going to take a little bit of a detour and tell you a little bit about this fat delta, because now finally I'm getting more people interested in this, but it would also be nice if you guys get interested, because I think this fat delta has a lot of potential, and who knows, maybe it's also useful for physicists. So what is fat delta? It's a kind of fattening of the simplicial delta, but it turns out that it's good to define it in a way that it's not very intuitive at first. Okay, so let's think about the category of epimorphism in delta. So the objects are the epimorphism, these vertical arrows with the double arrow here, and the morphisms are the commuting squares. The fat delta has objects, these epimorphisms, but the morphisms are the squares in which the top is a monomorphism in delta. Okay. Of course, when you just look at this, doesn't seem to be describing anything remotely intuitive. But here is a way to look at this. Think about an epimorphism in delta. Yeah, look at this picture here. This is an epimorphism from the ordinal 2 to the ordinal 1. And then you can say, look, if two things go to the same image, in this case, 0 and 1 go to the same image 0, then I think of the arrow from 0 to 1 as a special arrow, what we call a colored arrow, okay? So I think of this epimorphism as the ordinal 2, but in which certain arrows are special or colored. Okay, so what is this? This is what we call a colored category, or using Barwick and Kahn terminology, a relative category. So basically, what does it mean to have a commuting diagram of epimorphism? It means that colored arrows goes to colored arrow. Okay, this is elementary because it's the commutativity of this kind. So what this means is epimorphism in delta is the category whose objects are the non-empty colored ordinal, and the morphisms are the color-preserving functors between them. Oh, well, that sounds more intuitive, and it's actually how Joachim Koch defined it in this paper, except that to really technically work with this fat delta, it turns out that this category here, this description here, which is not intuitive, is actually more useful. Now, what does it mean to have a monomorphism at the top? So remember that the injective maps in delta are the ones you can use to define semi-categories. So how can you define the nerve of a semi-category? Is a functor not from delta up to set, but from delta mono up to set, whose Siegel maps are isomorphism. So what this means is that fat delta is isomorphic to the category of finite, non-empty colored, semi-ordinal, and color-preserving map. Okay? And you also have a map from fat delta to ordinary delta given by the target here. So what Koch did, let's stick to dimension 2, he says a fair to category is a functor from fat delta up to cat, such that X0 is discrete, so this is like the globularity condition, and all the Siegel maps are isomorphism. Now, if you took this definition and instead of fat delta, you put delta, that's a strict to category, right? So what Koch does, he uses the fat delta to keep all the compositions strict, but the fat delta encodes the weakness of the units, and this is really about this color preservation. Color preservation means those arrows in fat delta that are sent to identities by this pi becomes equivalencies of categories. Now, I don't expect that people can really understand all the details here, but I just would like to give you this message. Fat delta is a very, very nice category because it's a direct category. All the morphes go in the same direction. It's a category that allows you to kind of break up the composition structure and the unit structure. So you can somehow treat the two things as separate. Whether in the simplicial delta, they come together. Yeah. So in the simplicial delta, if you strictify the composition, you also strictify the units. In the fat delta, you can do the first one is strict, the second one is weak. So it's a very, very clever way to do this. And for a number of years, I felt I was the only person on earth that was interested in the fat delta. But this has changed. And in the last year, I've been collaborating with a group of people in Nottingham. They are doing type theory and homotopy type theory, who are extremely interested in the fat delta. Why? Because in type theory, it is good to have direct categories. And we are at the moment finishing a paper. I hope there will be a preprint on the archive soon, which gives a lot of new information about fat delta from the point of view of the theory with parities. So the result that I have proved in this paper, which is on the archive, is that these fair two categories are directly equivalent to weakly globular double category. If you see the way these functors are produced, and I haven't had the time to really give you the details, but I hope you believe me. So this X0, this category of objects and vertical arrows, is precisely the category of weak units. Okay, so the slogan is that weak globularity in dimension 2 is about the weak units. The conjecture is that this carries on to higher dimension. Why is this a big conjecture? Well, because it relates to Simpson's weak units conjecture. Yeah. So if one could prove that weakly globular and full category, which is my model that satisfies the homotopy hypothesis, is equivalent to fair n categories, so you have this theorem with an n instead of a 2, that would be a proof of the weak units conjecture, which has been opened for, I think, several decades in higher category theory. I haven't done it yet. I have some hope that we can get there. So I think that's probably it. I would like to give some time for questions, but I would like to also point out some references. So this was the Joachim paper, which as you see is 2006. This result about this last result here is in this preprint that has had many versions, and I believe I am getting close to the very final version. The paper with Pronk on the case n equals 2 was in TAC, and the book that does it for general n is this book that has this cover. This book also has some introductory chapters about multisimplicial techniques, which the reviewer said they could be really useful for PhD students. So if there are PhD students in the audience and you want to learn some multisimplicial techniques, even without the rest, I think they can be found in the book. And it also has introductory chapters where I give like the big picture in a way that is maybe even easier than what I have been doing in this talk. So I hope that that the book is written in a way that people can follow. This book was published during just before COVID hit, which was a little bit of a bummer in terms of, spreading the news. So if you like the book, feel free to get in touch. If you want to recommend it to other people, I would also be very grateful. And I think that's it. And I would like to hear from you if you want me to repeat something or you have further questions. Thanks very much for your attention.
Thank you very, very much, Simona. It was a very, very nice talk. I mean, really, very introductory and very informative talk.
Mm-hmm.
So, any questions or comments?
Just some appreciation. Really enjoyed the talk
Mm-hmm.
and picked up on several themes that were going on in there.
Mm-hmm.
I wonder if the n-fold nerve that you're talking about goes
Mm-hmm.
back to the nerve Robertson Street. Is that
Mm-hmm.
right?
No, it's a different type of nerve because so the Robertson Street nerve of strict and categories is a simplicial set.
Okay.
Yeah? So you basically have all the complexity squeezed along one dimension. And out of the nerve, then Dominic Verity introduced his notion of weak omega category. Okay. Whether what I'm doing here is in a sense a lot simpler, which is spreading things in ON different simplicial dimensions. So if we go back to this picture, yeah. So this is the nerve of a strict two category, whether Ross-Street nerve would be just a simplicial set. Now, one interesting question, and actually this is something I always ask myself. I haven't had the time to really work it out, but this is a bisimplicial set, right? So take its diagonal. So the diagonal would be like this. Yeah. I believe this diagonal maybe have some relation with the street nerve.
Right.
In fact, maybe this is also almost already in the literature. In some literature about bicategories. If you write to me an email, we can maybe chat over the email. I can we can see. I mean, but these are certainly not the same nerve because we are just working in different dimensions. Yeah.
Thanks. Thank you.
Mm-hmm.
Any more questions or comments? In the beginning of your talk, you mentioned about another approach followed by Emily Reil and her co-workers.
Yeah.
Is there any connection between your approach and their approach, or how they are related?
No, because I mean, you could ask this question basically for any other explicit model. Okay, I think that the person who is best to answer this question is Emily herself. I think both points of view can be very useful for different things. I think if you want to develop sort of very formal higher category theory, maybe the axiomatic approach is better. But if you want to sort of study concrete examples and maybe do some calculations, the modeling approach is more concrete. Let me say something. In fact, I put this in the abstract, and then I realized that there wouldn't be time to talk about this, but also to explain my abstract, because I forgot to say something. So let me come here when I talked about the n-fold groupoid case. Okay. Right, so this was, okay, so I talked about this functor, right, from spaces to this n-fold groupoidal structure. After this, more recently, well, very recently, because we submitted a paper a few months ago, Blank and myself used this for an application to homological algebra, and this is something I put in the abstract, except that then I didn't put it in the slide because I said it's too much. So what we did, okay, so there is a notion of cohomology of a simplicial category due to Dwyer, Kahn, and Smith that is defined purely topological. And this cohomology can be used to describe the K invariance of a simplicial category. So a simplicial category, you can think of it as a more grown-up version of a space. Yeah, you know what is Postikov decomposition of a space. You know what is the Postikov invariant. Well, these things exist also for a simplicial category. But what is the problem? These cohomologies defined topologically are quite untractable. Yeah. On the other hand, we like algebraic things because you can get a handle of them. And one way to do algebraic cohomology is under Quillen, yeah, which is very old in a way, but very important. So using this n-fold structure, we were able to write down an explicit resolution that we can use to compute these cohomologies. And so we have a purely algebraic description of this cohomology of simplicial categories. This is absolutely necessitates working with a concrete model. So it's also on the archive. It's the last preprint that I have with David Blanc. And it's a mix of categorical concept and simplicial homotopy theory. Blanc is more of a topologist, I'm more of a category theorist, and we collaborate for that reason. So this is an example of how an explicit model. Now, I can assure you that with a model-independent approach, there's no chance to do that. You really need to have something concrete that you can use to build a resolution. Our resolution was built from a comonad, which is something you write down quite concretely. So I believe both points of view, the axiomatic one and the model theoretic one, are useful just for doing slightly different things.
Thank you very much. Jenab, I think you have a question because you raised your hand. Yeah, you can ask your question. Unmute yourself. Yeah, you can ask, Jenab.
Yeah, what is the topological application of this techniques or this approach?
Well, the one that I just described, except that, as I said, I felt there were already too many slides, so I haven't put slides on this. This latest, I don't have it in the slides, but I mentioned something in the abstract. It's a topological application in the sense that we have managed to describe the cohomology, the Dwyer-Carney-Smith cohomology of a simplicial category, which is, if you want, is an infinity n category, using these models. So if you look at my preprint, I think that's fair to describe it as a topological application.
Thank you.
Any more questions or comments? Okay, so let's thank Simona once more.
Thank you very much.
It was a fantastic talk. Thank you so much.
Thank you. So feel free to get in touch if you like. And who knows, maybe we'll see each other sometimes. I've never been to Turkey.
Well, please, you're very welcome to visit Istanbul
Thank you
to
very
our
much.
institute.
Okay,
So,
thank you.
oh, you're welcome. So I will.
And I'm sorry that I was late with sending you the abstract, but the Christmas time was a little bit hectic because I had the flu, etc. But I
Oh,
had it
that's
on your
fine.
mind. I didn't
No
forget about
problem.
you. I'm really sorry about that.
No, no,
Yes.
no, no problem.
Okay.
Okay. So I will